This explanation is divided in 5 parts. The first part is an introduction. The second part will show with the computer that what you are going to learn really works. In the third part, you learn how to divide binary numbers by hand calculation. In this way, it will be easier to understand how the computer performs the division. The fourth part is the difficult one. It will be explained step by step how the subroutine that performs the division works. Fortunately, there's no need to know the machine code or the assembly language, because each command will be explained. Anyway, it will require a lot of attention, and maybe you'll need to watch this explanation of the fourth part more than one time to fully understand the content. In the fifth part, there are further considerations. We need to know that computers can do divisions in various ways, and today the modern computers do the division at hardware level. But in the 70s and in the 80s of the last century, the computers that the average people like me could afford had an 8-bit processor that could perform just the math operation of addition and subtraction only. So all the other math operations and functions had to be performed at software level. So when you print 10 divided 2 with an 8-bit computer, there's a subroutine that performs the division. In reality, also when we do 10 plus 2, there is a subroutine, but let's skip these details. Here, it will be explained the method of how a computer can do integer division using an 8-bit CPU. The 8-bit CPU is the MOS 6502 that was developed in 1965. The MOS 6502 is the CPU used by famous computers like the Apple I and the Apple II, the Commodore 64, the VIC-20, the BBC Micro, the Atari, and others 8-bit computers. Here it will be explained the code in assembly to make a simple 8-bit integer division. The requirement to understand this explanation is that you have to know binary numbers. Before to start the explanation, an example of an 8-bit integer division will be done using an 8-bit computer in order to prove that the subroutine works. Before to prove that the subroutine works using the computer, I have to explain how the numbers are stored inside the memory addresses. Each memory address is 1 byte, and each byte is a group of 8 bits. For example, the memory address 1500 is a group of 8 bits. The value 103 is represented in binary number as 1100111. So the value 103 will be stored in memory address 1500 in this way. Another detail that is required to know is that the hexadecimal machine code monitor that will be used to verify and display the subroutine for the division displays the number in hexadecimal format. The hexadecimal numeral system, shortened to hex, uses base 16. Here in the table we can see that 8 in decimal is 8 in hex, 9 in decimal is 9 in hex, while 10 in decimal is indicated as A in hex, and 16 in decimal is 10 in hex. Other useful values for our subroutine are indicated here in the table. Then, if we want to store the value 103 in memory address 1500, 1500 is in hex, we have to execute the basic command poke 5376,103. And after this command, we will have this. And if we want to know the content of memory address 1500 in hex, we use the basic command printpeek 5376. Now I load the subroutine for the division. Okay, here is the list. The subroutine starts at address 1400 in hex and ends at address 1419. Here, the things to point out are the following. The memory address 1500 stores the value of the dividend. The memory address 1501 stores the value of the divisor. The memory address 1503 stores the value of the remainder. At the end, when the subroutine has been executed, the address 1500 will store the value of the result of the division. Okay, let's try with a very simple division, 10 divided 3. So the result will be 3 and the remainder will be 1. Okay. Okay. Now execute the division. Okay, now let's check the result. Okay, the result is 3, and let's check the value of the remainder. Okay, now let's test the subroutine for a more difficult division. So let's try 177 divided by 9. Execute the division. Okay, now let's check the result. The result is 19 and the value of the remainder is 6. Now let's see if the result of the division is correct. Plus 6. Okay, 177. So we have seen that the subroutine works perfectly. Now we know that the subroutine works, and we know that computers use binary numbers, so we have to learn how to do binary divisions. In the next part, it will be shown how to do binary division by hand. So we are going to do 177 divided by 9 using binary numbers. Okay, this is 177 divided 91001. Okay, let's do the division. Okay, 10001 is bigger than 1, so the first digit is 0. 1001 is bigger than 10, so also the second digit is 0. Now let's compare 1001 with 101. We have still 0. Okay, now let's compare 1001 with 1011. Okay, finally 1011 is bigger than 1001, so we have 1. And let's do the subtraction. 0, 1, 0, 0. Okay, now let's use this 0. Let's compare 1001 with 100, and we have 0. Now let's compare 1001 with 1000, and we still have 0. Okay, Now another 0. Now let's compare 1001 with 10000, and 10000 is bigger than 1001, so we have 1. And let's do the subtraction. Okay, that is 1 1 1 0 0. Okay, so let's use the last one, and 1001 is smaller than 1111, so we have another 1. Let's do the subtraction. 1001, and finally the remainder is 1 minus 1 0 1 1 0. Okay, so the result is, this is 16, this is 2, this is 1, 16 plus 2 plus 1 is 19. So the result of the division is 19, and the remainder is 4, 2, 4 plus 2 is 6, and the remainder is 6. Okay, so now I want also to indicate the values that we compare the divisor. So we compare 1001 with for the first digit with 1, with 10 that is 2, with 101 that is 5, with 1011 that is 8 and 11. Then we made the comparison with 1000 that is 4. Then we made the comparison with 1000 that is 8. Then we made the comparison with 16. 1, 2, 3, 4, 5, 6, 7. And finally we made the comparison with 15. Okay. 8, 7, 6, 5, 4, 3, 2, 1. Okay. We'll check these values later. Now we call the groups of bits inside the red rectangles the values inside the accumulator. The accumulator is the most important register of the CPU. It's the register where we can compare values, we can add values, and we can subtract values. So we can compare the value of the accumulator with the values of the divisor. If the accumulator is smaller than the divisor, we continue to increase bits from the dividend. While if the divisor is smaller than the accumulator, we subtract the divisor from the accumulator. We increase another bit to the accumulator from the dividend, and we place a 1 in the proper bit of the result. And this procedure is repeated 8 times. Now it's time to explain how the subroutine for the division performs this procedure, and this is going to be the difficult part. Now we have to remember that the dividend is stored in memory address 1500, the divisor is stored in memory address 1501, the remainder will be stored in memory address 1503, and the result will be stored in memory address 1500, so the value of the dividend will be lost. When we run sys5120, the CPU starts the subroutine. 5120 in decimal represent 1400 in hex, so sys5120 jumps to the hex address 1400 and our subroutine begins. We know that we have to do 8 comparisons, so 8 cycles. And in order to count 8 cycles, the X register of the CPU will be used as a counter. First instruction is LDX08. This means that we load the X register with the value 8. It's been already introduced the accumulator register of the CPU. The accumulator is the register that we'll use to store the significant bits of the dividend that have to be compared with the divisor. LDA0 means that we load the accumulator with the value 0. ASL 1500. Before explaining the ASL extraction, it's necessary to introduce a very simple concept. The CPU 6502 has a status register with some bits used to flag certain conditions. For our division subroutine, we care of just two flags. These two flags are the carry flag and the zero flag. The zero flag and carry flag are both a simple bit that can have the values 0 or 1. ASL arithmetic shift left. ASL 1500 shift left all the 8 bits of the memory address 1500. The rightmost bit, bit 0, is filled with a 0, while the content of the leftmost bit, bit 7, go inside the carry flag. Hence, the information of the leftmost bit is not lost. It's very important to point out that the rightmost bit is filled with a 0. It was previously said that at the end, the memory address 1500 will store the result of the division. It's not possible to understand it now, but it will be clear only at the end of the explanation. But this 0 that is going to be inserted here with ASL represents the same 0 that was written at the beginning, after the first comparison of our division. Don't worry now, it will be clear later. ROL, rotate left. Rotate left is very similar to arithmetic shift left. The important difference is that the rightmost bit is not filled with a 0, but is filled with the content of the carry. In this case, rotate left is applied to the accumulator. So, the combination of arithmetic shift left plus rotate left is very powerful, because this allows us to select the important bits of the dividend that have to be compared with the divisor. In fact, before explaining the next instruction, it's important to clarify that this is the first cycle of our subroutine, and for the second, the third, and also the fourth cycle, the repetition of this sequence, arithmetic shift left 1500 plus rotate left, allows to select in the accumulator the most significant bits of the dividend. Well, now in our accumulator, we have selected the first bit of the dividend, and we have to compare this value with the value of the divisor. In order to do the comparison, we have the CMP instruction. CMP 1501 means compare the value of the accumulator with the value of the divisor that was stored in memory address 1501. Clearly, this CMP instruction has to produce an output that informs us if the value of the accumulator is bigger or equal or lower than the value of the divisor. And the output is that if the value of the accumulator is higher or equal than the value of the divisor, then the carry is set to 1, while if the accumulator is lower than the value of the divisor, the carry is set to 0 or carry clear. For the first cycle, but also for the second and for the third cycle, the divisor is bigger than the value of the accumulator, so for the first 3 cycles the carry is clear. Now that we made the comparison, we have to choose what to do according to the result of the comparison. As we saw during the division by hand, if the divisor is smaller, we subtract the value of the divisor from the accumulator and write a 1 in the proper position, while if the divisor is bigger than the accumulator, we simply add a 0. The next instruction, BCC branch carry clear 1413, allows us to choose what to do according to the result of the comparison. Branch carry clear 1413 jumps to the address 1413 if the carry is clear. We know that for the first 3 cycles the accumulator is smaller, so the CMP make a carry clear and consequently BCC branch at the address 1413. So it skips the 2 next instructions. That are the instructions that perform the subtraction and write a 1 in the result. So for the first 3 cycles, no subtraction and we don't write a 1 in the result. Hence, we jump to the address 1413. Practically, at this point, the cycle is concluded, and we know that we have to repeat each cycle 8 times. We said that we use the X register as a counter, and for the first cycle the value is 8. At memory address 1413, the instruction DEX decreases the value of the X register by 1. So now we have X equal to 7. In this way, after 8 cycles, we have X equal to 0. When X reaches the value 0, the 0 flag is set to 1. The 0 flag was introduced previously. This change of the 0 flag from 0 to 1 clearly has the purpose to alert us that the counter has finished to count. In this way, we can take the proper action if X is 0 or different from 0, and obviously the next instruction is the one that takes into account if X has reached 0 or not. BNE 1404. BNE branch on not equal to 0. BNE instruction branches to memory address 1404 if the 0 flag is clear. In our case, if X register is different from 0. So the BNE instruction allows that the subroutine repeat the loop. We know that for the first 3 cycles the BCC instruction makes the branch, but for the 4th cycle does not branch. So we can explain the meaning of the 2 instructions that have been jumped for the first 3 cycles. At the 4th cycle, the accumulator is bigger than the divisor, so we have to subtract the divisor from the accumulator. The instruction SBC 1501 subtracts the value stored in memory address 1501, that is the divisor, from the accumulator. So, for the 4th cycle, subtracts the value 9 of the divisor from the value 11 of the accumulator. After the subtraction, we know that we have to write a 1 in the result. Next instruction has the purpose to do this. But it's here that we have to pay attention, because the next instruction do not write the 1 in the proper position. The next instruction is INC 1500. INC means increment memory content by 1. As we said, 1500 at the beginning stores the values of the dividend and after 8 cycles stores the value of the result. At the 4th cycle, the address 1500 has the following value, because the arithmetic shift left has been applied 4 times. After the increment, it assumes the value 0001, 0001. So we have the 1 at the last position, that is bit number 0, but we want that our 1 has to be in the 4th position, bit number 4. So what happened? We know that the subroutine has to do further 4 cycles, so the arithmetic shift left 1500 is applied other 4 times before the end of the subroutine. And after we apply arithmetic shift left another 4 times, we have 1500 with the most important bit, that is 0001. So at the end the 1 is placed in the correct position. At this point, it should be more obvious that the 0 that was inserted in the bit 0 of the memory address 1500 in the first cycle, after other 7 cycles, represent the first 0 of the result. Now all the instructions inside the cycle have been explained. After 8 cycles, x is 0, the 0 flag is set and the B&E instruction doesn't branch. Now the value inside the accumulator represents the remainder of the division, and if we don't want to lose this information, we have to store it in some memory address. For this reason, the next instruction is STA 1503. STA means store the value inside the accumulator in the memory address 1503. Now everything is done and we have to come back at the point where we called the subroutine. So the last instruction is RTS, return from subroutine, and in our case it returns at the command line in BASIC. Now that all the instructions have been explained, it is possible to verify step by step that the content of the accumulator after each cycle and before each comparison is exactly the same of what we have anticipated after the division by hand. The Wigmon cartridge allows us to check the content of the X register and the accumulator after each cycle. Now we store the values of the dividend and the divisor inside the memory addresses. We start the Wigmon. And we load the subroutine for the integer division. Finally, it's possible to execute the line of code step by step. Okay, we already executed the arithmetic shift left and the rotate left. And before the compare instruction, let's check the content of the registers. AC is the content of the accumulator and XR is the X register. Now we execute the compare instruction, the branch carry clear, and it's possible to verify that the BCC jumps to the address 1413. Second cycle, X is 7, accumulator is 2. Third cycle, X is 6, accumulator is 5. X is 5, accumulator is 11, and 11 is indicated as B in hex. And now that the value in the accumulator is higher than the value of the divisor, the carry is set after the compare instruction, and in this cycle the subtraction and increment instruction are executed. Fifth cycle, X is 4, accumulator is 4. Sixth cycle, X is 3, accumulator is 8. Seventh cycle, X is 2 and accumulator is 16, and 16 is indicated as 10 in hex. Eighth cycle, X is 1 and accumulator is 15, and 15 is indicated as F in hex. After 8 cycles, the subroutine ends and it's possible to check again the results. We have seen how the subroutine works, but it's clear that this subroutine has a very limited range of applicability. In fact, it works only with positive integers from 0 to 255. In fact, the highest value for an 8-bit integer is 255. So, if we need a wider range of applicability, we have to rewrite a subroutine that handles 16 bits that are 2 bytes instead of just 1 byte. With 2 bytes we can extend the range till up 65,535. But for each number, dividend, divisor and remainder we have to use 2 bytes instead of 1. And I used a 16 bits subroutine on my previous video for the determination of the prime numbers till up 1000. This subroutine always does 16 cycles instead of 8, and each cycle is longer compared to the 8-bit subroutine, so it takes more time to be executed. Then, another aspect is that we can extend the range, but we are always working with integers, while most of the time we want the result represented as a floating point number. And here is a subroutine that takes 2 integer values and writes the result as a floating point values. We can notice that this subroutine is a lot more complicated than the one used for the integer division, and it uses more resources, both in terms of time and memory. So, to conclude, when we need more accuracy, we have to use more resources. So, when we want to optimize speed and memory, it is better to use the subroutines that better fit the requirements of our programs.